All right, hello everybody. In this take on Professor Carbon, what we're going to do is we're going to go over two problems. Both of these are going to be in what I would consider the advanced arena, and both of them are going to address some issue of chemoselectivity, that is being able to selectively react one functional group in the presence of a very similar second functional group. So the first problem is shown here, and what it is an oxidation with the reagent MnO2, or manganese dioxide. Now, many of you may be much more familiar with the similar reagent, potassium permanganate, KMnO4. And potassium permanganate is a beautiful purple molecule. When you put it in solution, it is just an incredibly gorgeous color. And permanganate, KMnO4, is a much more powerful oxidant than MnO2. Actually, it turns out MnO2 is kind of an ugly rust color, and it's typically the byproduct that you get from using permanganate. And so why would we choose to use this more mild oxidant of manganese dioxide? Well, it's going to give us some form of selectivity. And just like permanganate, which is a powerful oxidant, MnO2 is still an oxidant. And so we're going to oxidize one of our functional groups here. And if we think about it, we actually have four functional groups that could be oxidized. So we know permanganate, KMnO4, in the presence of alkenes will actually dihydroxylate them and then cleave the carbon-carbon bond in between. And so it's a cool way to make carboxylic acid. So if you're unfamiliar with that, look up how potassium permanganate reacts. Thankfully, MnO2 does not typically react with alkenes. And so because of that, we can X these two sites off as sites where MnO2 may react. Being said, we still have two different sites that have alcohols, and both of them in principle could be oxidized by an oxidant like MnO2. But in this particular case, we're only going to get oxidation of one of the two alcohols. And so I will draw what that looks like now. We're going to make this ketone. We're going to have the other alcohol is going to remain unreacted. And so that's pretty surprising, especially since the top alcohol is the primary alcohol, and so we might consider it to be slightly more sterically accessible. So to explain this kind of chemoselectivity, what we have to do is turn to our bond dissociation energies, or BDEs. And if you remember, a bond dissociation energy is the amount of energy that needs to go in to break any given chemical bond into its pair of radicals. And so the BDE is a measure of bond strength, and it can be used as a gauge for how reactive functional groups are. Sometimes people like to interpret it as how stable the corresponding radical is. I try not to think about it in terms of radical stability. Instead, I try to think about it in terms of bond strength. And so I usually tell many of my more advanced students that, if you're going to memorize any bond dissociation energies, there's a couple of really good ones I'd encourage you to remember. So one of those is methane. And so the bond here is the CH bond in methane, comes in at about 104. And so I would encourage everybody to know that because it's a really good benchmark. And the units on a bond dissociation energy are typically in kcals per mole. And I apologize for those of you that prefer kilojoules. Remember, 4.18 is the conversion from kcals to kilojoules. And so you can always just multiply if you prefer kilojoules. For whatever reason, organic chemists have stuck with kcals. And because we've stuck with it, all students kind of learn it in kcals. And so thus the system continues. Okay, so 104 is for methane, and that's a really good benchmark. And it turns out delta, more than about 3 or 4 kcals per mole becomes a very significant difference in energy. So it's really hard to benchmark these because they're just kind of a unit that we don't deal with in everyday life. So we get used to, inches and miles and liters. I mean, these are units that we encounter every day, but kilojoules per mole isn't something that's inherently intuitive. So I usually tell folks that 3 to 5 becomes a really big deal. Okay, then the next one up here is going to be ethane, and I typically don't memorize these other ones. I tend to have to look them up. But what you'll notice as you add substituents to that carbon, that bond dissociation energy goes down. And the delta here is about 3, and the delta here is about 3. And so again, most people justify that by saying that the secondary isopropyl radical is more stable than the methyl radical. And again, I wouldn't choose that interpretation. I would instead prefer you say that the bond is stronger in methane than it is in propane. But however you choose to describe it is ultimately up to you. So it turns out adding those substituents adds quite a bit of stabilization energy. So for instance, the difference between the methyl groups in propane, which we have several, and that secondary carbon is a very real difference. It also turns out having alpha heteroatoms makes a big difference. And so if we're talking about alcohols, we might consider what ethanol looks like. And so now we have the CH bond in ethanol, and this one comes in at 96. And so if we compare that really quick, so this is a CH2 containing carbon. We contain that up here to that CH2 containing carbon. We'll see that it's a pretty decent drop, a couple of kcals per mole, which again is significant. So having that alpha heteroatom can be quite real. Now, all in all, these are relatively small changes. And for those of you that have been through the section on resonance, you'll remember that, if we have something like the allyl radical, we can have a resonance structure where that radical is delocalized to the other carbon. And when you can spread out that radical, ultimately you can make a more stable radical, and that usually makes it more stable. Okay, and so that should then translate to our bond dissociation energy in a molecule like propene, and it turns out that is true. So the bond dissociation energy in propene is 88, and if we compare that here to our primary carbon in ethane, now all of a sudden that's an incredible difference. So delta here now is 13. And so that indicates that this resonance effect has a truly massive effect on the reactivity. So remember I said 3 to 5 is a big deal. Well, this is well above that. So if you want to put it in terms of big deals, we could call this 3 big deals worth of energy. All right, and just as we might predict from our green swirl up here by comparing ethanol, if we look instead at allyl alcohol, so OH, and add that extra OH group on there, this one now comes in at 82. And so again, by having this alcohol group here, we've significantly stabilized that energy. And so it turns out these allyl alcohols have very low bond dissociation energies, and that makes them much more reactive than standard primary alcohols, especially to reactions that remove that CH. And by the way, the reaction doesn't need to be a radical reaction. So it can be other forms of reactions as long as that transition state energy reflects the weakness in that bond. And so in this particular case, we have one allyl alcohol here, and we have a primary alcohol. And so in this particular case, the allylic OH wins out. And this is a really nice feature of the molecule manganese dioxide. So if this is a reaction that's new to you, often synthetic organic chemists will choose to use MnO2 when they want to selectively oxidize an alcohol, which is either allylic or benzylic. And those are really the special kind of window of reasons why we would use MnO2. It turns out to be a very nice reaction. It's quite generalizable, and in the lab it's relatively easy to conduct, which is another reason why we really like it. So overall, hopefully that helps explain the chemoselectivity for an allylic alcohol that you can observe by using manganese dioxide as your reagent. So we got a second problem here, and in this particular case, we have the very similar product from what we saw above, and so this is a compound later in the same synthetic sequence. And in this particular case, the authors are going to choose MCPBA as a reagent, and if we can remember, that is metachloroperoxybenzoic acid. And the most common reaction that we know of for MCPBA is to convert an alkene to an epoxide, and it would help if I didn't put a double bond here. And so that is our most common reagent. Now, the hiccup with that is for this reaction to work, we need the alkene to be a nucleophilic alkene. And so if you look up here, there is an alkene, but if we look a little bit further, that alkene is contained in an alpha beta unsaturated ketone. And so remember that ketone is electron withdrawing. And so if I go to a new color here, I can help illustrate that. So we have our alpha beta unsaturated ketone, and we can imagine a resonance structure. And we can have a nice another resonance structure. Okay, and so these alpha beta unsaturated carbonyls are really withdrawing a lot of electron density from the alkene. So instead of being a nucleophilic alkene, usually these alkenes are attacked by a nucleophile, and we call them electrophilic. So if that alkene is a nucleophile, we might consider this alpha beta unsaturated ketone to be an electrophile. And so it's fundamentally different or opposite in reactivity. So it turns out these alpha beta unsaturated double bonds tend not to be oxidized with MCPBA very well because they're mismatched in terms of their reactivity. Now, there is a second reaction that is taught typically much later in the year when we talk about unique ways to make esters, and this is the Baeyer-Villiger oxidation. And what's nice about the Baeyer-Villiger oxidation is it will take a ketone and it will add an oxygen just smack dab right in the middle of that carbon-carbon bond. And so that's a pretty cool reaction overall. And it's a really unique, fun way to make an ester. Now, there's a fundamental problem with this Baeyer-Villiger oxidation, and that is if your ketone has two different sides associated with it, we have to pick which one of these two carbon-carbon bonds end up being broken and have the oxygen stuck in the middle. And it turns out that feature is something that you can look up. It is called the migratory aptitude. Loosely associated, it kind of similarly follows carbocation stability. Not exactly, there's a couple of curveballs in there, but in general, tertiary moves better than secondary, which moves better than primary. And so overall, if you had to guess without memorizing it, I would go carbocation stability. If you have time though, totally look it up in a table. So again, migratory aptitude. Now, in this particular molecule that we're referring to up top here, we have a conundrum because not only do we have that alkene that we already discussed might be a poor reaction, but we have two different ketones to consider undergoing the Baeyer-Villiger oxidation. And so that means there's actually up to 4 different carbon-carbon bonds that could be cleaved. So I'll squiggle through those right now. And so if we use our migratory aptitudes, we can kind of erase 2 of these options. So if we look at the ketone on the left side, we'll notice it's primary to the methyl, or it's got a secondary carbon or tertiary carbon on the other side. And so based on migratory aptitude, it should go that way. Same thing is true over here. And in this particular case, the alkenes usually are really poorly migrating groups. So we might predict that it would move in that manner if it reacted with that ketone. Now, it turns out in this particular case, the product is actually going to be from the one on the left. And so we are going to have, oh, and by the way, another really nice feature about this reaction is the stereochemistry stays. So that's pretty nifty. And so the wedge is going to stay a wedge. And so that's pretty awesome. So we're going to end up with this product. And so the green bond over here, which I'll now exaggerate a little bit more, that's the one that's going to eventually be cleaved. And so some of you then may ask, why one ketone and not the other ketone? Well, we already spent some time talking about this effect of being alpha beta unsaturated. And it turns out in the Baeyer-Villiger oxidation, we need to break conjugation with the ketone. So, and I'm just going to put R groups over here for simplicity. this is going to be in equilibrium with a tetrahedral adduct. And I'm going to write AR for my metachloroarene. So we'll just label that up there, AR. And so this is the adduct from which this reaction goes. And if we think about this in the context of an alpha beta unsaturated carbonyl, this one is conjugated. And if we have our same equilibrium here, this is not conjugated anymore. And so if conjugation makes that product more stable, and both of these have the same kind of energy in the intermediate, then if we think about it, this jump up should be smaller than the more stable leap up. Okay, so you got a little bit of a hop from the normal one, and then because we've stabilized the starting material, it becomes quite a jump up. And so because of that, we need to think about putting in more energy, and anything with more energy will be a slower reaction because it'll have a higher transition state associated with it. And so by being required to break the conjugation with that double bond, we actually can get pretty good selectivity for a single product. So all in all here, we've discussed two different issues of chemoselectivity, and hopefully we've reviewed a whole bunch of fun stuff along the way, including our bond dissociation energies, some fundamental issues with both nucleophilicity versus electrophilicity, but also some issues of resonance and reminding people how resonance really affects the molecule overall. So with that, thank you for tuning in to Professor Carbon. Please see our other videos. As a reminder, these are all color-coded. So if you look across the top here, you can get the kind of functional group or reaction that you're looking for, and then the kind of question is kind of labeled over in this part. So with that, please go on and enjoy your day, and thank you for tuning in.